this tutorial, we'll be talking about C++. C++ got pretty hard those days. It grew up a lot. It got a lot of features from other languages. Also, it improved its own features. So C++ those days is a very complex language, but also very flexible, powerful. And in this talk, we will have an overview of important features of the modern C++. And those are the funny memes you can find online if you Google learn C++. C++ is all about abstractions, nothing else. We know that we always compile programs for bare metal, but bare metal only understands instruction set architectures and assembler, like machine code that is compiled from assembler. So with assembler, we can actually do anything. We have the whole control over machine, but coding is very hard because it does not provide abstractions. Things are a little bit easier with C. C is basically, we can also think about C as a kind of assembler in the way that it also gives us the whole control over the machine. But C gives actually much more abstractions than assembler, but it's still not as easy to code in C to write especially hard, complex programs, because C's abstractions are pretty simple. It's like functions, variables, pointers, structures. So those are pretty simple things that do not help with complex programs. It's an opposite to Python. Python provides great abstractions, so everybody can just learn Python within a week. It's super easy to start programming in Python, but Python is quite limited. It is also limited not only in functionality, but also in performance. We all know that Python, for example, for machine learning, Python is just like, it's an interface, but the actual machine learning algorithms are written in C++ underneath Python. So C++ is somewhere in between here in this hierarchy. So C++ provides you with very powerful and nice abstractions that are much more advanced than C. So you can write much better programs. But it's only if you know how to use those abstractions, because they are pretty complex, actually.
Ask a question?
Yes.
So in Python, what kind of functionality is limited?
It's mostly performance. And also, you don't have like bare metal control over machine. You cannot tell me that you want. If you want to call some like system call library, you'll have to use a C++ wrapper or something.
Okay, so it's more about like system.
Does that make sense?
Sure. Okay.
I hear it too.
Saying that with Python, you probably cannot control the memory layout, right? You don't have pointers, right?
No, in Python
you cannot control memory layout. But yeah.
In Python, you cannot directly, but there is something called Cython that actually allows you to alter the memory layout.
Okay.
But do we really need to control that?
Yes, for performance.
Okay, so like for functionality,
it depends what you're writing. Yes.
So pretty much all the high performance Python libraries are written in C++.
Sure. Okay.
Right. But you need to know how to use C++ because the abstraction is pretty hard and it's easy to break things if you don't use them properly. So why do we need abstractions in general in the context of programming languages? So the first, one of the main things we need abstractions to simplify development. So we want to have a framework that would allow us to briefly and more efficiently express things that we want to write. Also, we want them to make code safer because at the bare metal level, when we have the whole controller machine, it's good, but at the same time, it's pretty violent. You can break things easily, and you need to be more careful when writing code like that. So programming languages, we want from them to provide some safer abstractions that would protect programmers and also users from bad things happening. And at the same time, from programming language, we want to have it portable. So so basically it's the same programming language for different systems. So those are the main three things that I came up with. Maybe, I mean, for sure there is more, so we can think about it, but those are the most important, I think. So let's briefly see the evolution of C++. So C++ was created in 1985 by Brian Stroustrup. In 1998, C++ got STL. STL is called Standard Template Library. That's the library that defines all the C++ algorithms and data structures, such as vectors, queues, sorting algorithms, mathematical algorithms, and so on and so forth. A little bit later, there was another library introduced. It's called Boost. This library was pretty popular among C++ developers like 10 years ago. It's still popular. So it was introduced as an alternative to STL, but it was growing initially much faster than STL. So it got much more features and libraries for C++ than the original library. And then starting 2011, C++ has been consuming all features from Boost. Basically, this library started merging, and it also started consuming features from other languages, especially functional languages, developing its own features and growing as never before. So what do we mean by modern C++? We mean the C++ that appeared after 2011. So this is the brief overview of the C++ evolution, starting the original standard, starting like 1998 standard, and up to the most recent standard introduced in this year with all the features that came out. So what is C++ standard? How is C++ defined? C++ is defined by the standard. Standard is basically specification for the language. So this is a paper that tells what the language can do and which features it has. The compilers, such as GCC, ICC, LLVM, just implementations of the standard. The standard defines syntax of the language features, memory models, algorithms, containers, data structures, and everything about the language. The standard is being developed by the C++ committee that consists of software developers, PL faculty, hardware developers, and all the experts that know about C++ everything. So they occasionally meet. So for example, this is a picture from their meeting in 2017, where C++ 17 was introduced. They occasionally meet and decide which features should be included into the language and where the language should move. Here. Okay, so how to get access to standard? So first, you can pay and buy standard from ISO, or there is a free draft here. You can get free drafts of the standard. There are exact copies of the original standard. They're for free. You can get them from here. But it's pretty hard to understand the standard because it's formally written. So C++ developers normally use online resources. I'm pretty sure most of you who ever written programs in C++ are familiar with those two sources. Here is basically interactive version of the standard where you can easily understand what's going on and how to learn about C++. So let's get started. In this tutorial, we will see some features, like very few features, because C++ has tons of them, like basic features that came in C++ 11 or later. We will see some features from memory management, such as NullPointer, SmartPointers, type inference, some features improving concurrency. We'll see the C++ memory model and memory consistency, also futures and promises. And we'll see some additional language features, such as Lambda expressions, const expressions, and the moving semantics, and also R-value reference. Yeah, so NullPointer. So NullPointer first appeared in C++ 11 in order to strengthen the abstraction around zero pointers. All you know originally in C, and also in the first versions of C++, if you want to assign pointer to a zero address, basically pointer to nothing, you're supposed to use the null keyword. But unfortunately, null is not a zero pointer abstraction. Null is just an integer. If you see how null is implemented in C++ library, it's just zero. It's an integer literal that is casted to void pointer. So this is not an abstraction, and there is multiple issues here. Consider you have three functions that have the same name, but they have different arguments. One function accepts an integer, another function accepts a pointer to an integer, and another function accepts, for example, a Boolean argument. If you try to call this function in the old way, like using null, you'll get a compiler error because the compiler won't be able to identify which function you want to call, since null is it's the same null for both pointers and integers. So it will be confused between the first two functions. Same issue appears here when you have a class with two constructors that accept different arguments. The first constructor accepts an integer, the second one a string. So those are two completely different constructors. So this code will not compile because of the null here. So NullPointer is an abstraction. So it's an abstraction about zero pointer, same purpose as null, but this is not a casted integer. NullPointer is actually an instance of the C++ runtime class that is called C++ NullPointer_t. So this is actually a class in the C++ class hierarchy. And if you now try to compile the code like this with two different constructors, but you put NullPointer here, you won't get an error. The compiler will disambiguate this instantiation. It will understand that NullPointer is actually a pointer and will call the proper constructor. So the rule of thumb here, you should never write null in C++. You should always write NullPointer because this is a stronger abstraction to express dangling pointers.
Nikita, I have a question.
Yes.
Go back to the previous one.
Yes.
Yeah. So when you say string S1, so which constructor it will call?
The second one.
And why is so?
Because NullPointer is a pointer. It's not an integer.
Oh, okay. So because of that constant character is a pointer, so that's a match.
Yes, exactly. But here, in this example, it's not a match because null is actually an integer.
And so it matches with, so null is both, so integer means it can be either the unsigned integer 32t or the next one. So there is the confusion.
Yes, exactly.
Okay.
Yeah.
Yeah, so it seems like now it's a bug, right, before. And we just introduced the null pointer to solve this bug.
It's not like
because basically you have two types of, like, you can be an integer or a pointer.
It's
I
not
wouldn't call it
as you defined, right?
But now, yeah, but for this example, right? So you will get an error,
which is fine, right?
Yeah.
Which is fine. So you just modify your program.
Yeah. But now basically you can avoid this.
Okay. Right.
Yes, it's totally fine here. It's not like the compiler will tell you it won't be able to disambiguate function calls, but it's okay. You can have a situation like this. What it means, you need to strengthen your abstractions. That's what they did with NullPointer.
Okay, I see. Yeah.
Yeah. So this is not a bug. It's just a way to allow more things in language. Okay.
Nikita,
any more questions? Yeah.
Nikita, so I'm assuming that could you show the figures in the slide? Not in the previous slide. So next slide.
Oh, next slide. Okay. Yeah.
Yeah. So I'm assuming that there is some like automatic type conversion going on over here when you call this constructor, right? So just to clarify, so character star is not an instance of any class, or is not any class type in C++,
no.
right? Okay.
It's a pointer, yeah.
So basically when you call this, so the compiler is actually converting NullPointer into this. Into a constant character star, right?
I'm not actually sure if we have implicit type conversion here. We'll have to see what is std NullPointer_t exactly, how this structure is defined.
Okay.
That's I'm not sure. You can get it from standard.
Okay, thanks.
Yeah. Okay. So if no more questions, let's move to more important things. So let's move to SmartPointers. So SmartPointers were initially introduced in the Boost library, and they were brought to C++ with C++11 and C++14. So SmartPointers came in order to make memory management simpler and safer. Can anybody tell me what's the issue in this piece of code?
Yeah, I think the issue is that you use a new, but you did not delete.
Right. And someone said, yes, delete is missing here. So we basically have memory leakage because we allocate memory in this line, but we forget to delete it. When the function is exited, it's terminated, the memory is handling. So there is memory leakage here.
So Nikita,
Okay.
is not there any automatic garbage collector kind of thing that can like occasionally wipe out all these leakage? I think something like
Right.
that happens in Java, right?
Right. This is the purpose of smart pointers.
Okay.
Yes. Also, if we put delete here, so like let's put delete before return sentence, return here. So will it actually solve the problem? Is it enough just to put delete before return?
Well, do you have to set the pointer to a null value after you delete what it's pointing to?
No, it's not actually necessary.
Maybe like a dangling pointer?
No, it'll be fine. The function will exit, so the pointer the pointer data only lives in this scope. So when the function is terminated, we cannot access data anymore. So we should not worry about this data anymore. So the issue here, actually, there is a function call. So in this example, ECD sort. A function call might actually throw an exception. Something might happen, like an error or whatever. So the function can just terminate in the middle. And since we're not handling exceptions here, the outer function, compute percentile, will also terminate. And it will terminate actually before we delete stuff. So in this case, even if we have delete before return, we will still have data leakage because the function will terminate at this level. So basically, this is just to show why manual memory management is very complex, because we have to consider all possible executions of the program, including failure executions, and make sure that we remove memory everywhere where the program can reach. So doing like reaching analysis by hand is very hard. So that's why we need some memory management system like in Java or Python to handle the stuff better. So C++ introduces smart pointers.
Let me ask one more question to the group. Just want to make sure that.
Yeah.
Right. So what if we do not delete? Right. So what's wrong with not deleting this?
So you will have some dangling pointer. Your memory will not be wiped out. And once you get out of this compute percentile, there is no way you can access and clean up that memory. So at some point, you will run out of your available memory. So the program will crash.
Right. At a certain point, right? But yeah, it may not crash right away. So that's actually true. Okay. In some cases, the increase of the memory footprint may not be that obvious. So there are some certain tools to help you debug things like this, like Valgrind. Right?
Yeah.
Okay. All right. Good.
Okay. So let's see how we can solve it with smart pointers. Oh yeah. So before C++ defines 3 types of smart pointers. Actually, we'll discuss all of them: unique pointer, shared pointer, and weak pointer. So let's start with the unique pointer. This is the simplest one. So the unique pointer is just a simple replacement of the unsafe pointer. I made a simple wrap on top of an integer here. This is, we call it myInteger. It's a class that wraps up integer just in order to allow us to see where the integer is being constructed and deleted. So the constructor has created, the destructor destroyed, and also operator equal and get integer functionality. So this is a wrapper on top of integer just to see the process of constructing and destructing. So this is our function boo, and let's say we want to allocate memory for my integer. So we create a unique pointer of my integer that we call data, for example, and we make it unique. So by std make unique function. So data is the same pointer to my int as like a normal pointer that is expressed with my int star. However, this pointer is managed by the unique pointer class. So what it means that when the function is actually exited, we will have the allocation of the memory. So when the function boo is terminated and the data variable goes outside the function scope, the memory for the integer will be removed. If we run this program, we can see then when the program starts, the pointer is created, then we see the output of data 10, then the function is the function is exiting, and the memory is being destroyed. So we don't need to manually worry about memory. We can just forget about it. So the smart pointer will ensure that the memory is properly deallocated. So the std make unique.
How do you handle that exception case here? Like you said that there could be an exception in the function call that's call inside. In your
Yes.
previous example, you have that standard : sort, right? So if there was an exception, you would have an
Yes.
issue. So how you handle that particular exception here?
So here the smart pointer will trigger deletion of memory when the function boo is exited, no matter the reason. So if it's exited because of exception, it will still be called. It will still be
Okay,
destroyed.
so the smart pointer is actually taking care of all possible that execution that previously was taken care of by the user.
Yes. So the smart pointer is destroying when data, like the scope of data, is finishing.
Regardless
So
of
data,
the proper finishing or finished by an exception, it will get
exception
destroyed.
is fine. Yeah, exception is fine because when exception is thrown, the function is terminated.
Okay.
Yeah. So the std make unique is example that came a bit later. So before in C++ 14. In C++ 11, people used to allocate memory with new operator, even for smart pointers. But then people decided that new operator is kind of old and it assumes that you need to manage memory manually. So they just replaced it by std make unique. Another important thing that unique pointer gives you is ownership transfer. That's something that you cannot do with raw pointers. So let's say you want to transfer, you allocated memory in one object and you want to transfer this memory to another object, but you don't just want to transfer data, you also want to transfer ownership, which means you want to transfer responsibility over this memory. So this is something you cannot do with the raw pointers, but you can do with unique pointers. This is an example. So in this example, we have the function foo that accepts a reference to a pointer. And inside this function foo, we create a data using SmartPointer. So that's the same as we did before. We create data, but then in the next line, we move the ownership of this data into the pointer that we have here as an argument. And if you see where the function foo is called from, it's called from the main function. So in the main function, the function foo accepts the reference to another smart pointer that is defined in the main function. So actually we have two pointers here. One is inside foo function, another one is inside main function. So the memory is being allocated inside the foo function, but then we transfer ownership into the outer scope, into the main function here, data, and this is possible because of this std move construction that is called moving semantics. So if we have time, we'll also talk about this later.
Nikita, if you don't use the standard, this std move, compiler will error out?
Yeah, it will be error because operation equal is not defined. It's not defined for unique pointers.
So what is the use case of this transfer ownership? I mean, why would I do the make unique thing inside the called function instead of doing in the main? What is the simplest, most use case of this particular code pattern?
For example, you have a function. Okay, let's say you have a function that that is called like create money. So the function that creates money and returns money. So you create money inside the function, but then you need to transfer this money, like both the money itself and the responsibility, like ownership of the money, to someone who is actually calling this create function or create money function. Okay. So you are creating the function, you are allocating money inside the function, but then you need to transfer it to the object that called this function, right?
Okay.
Does it make sense?
Yeah.
It's like there is the design pattern. I forgot how it's called. Factory. It's called factory. So that's a design pattern where you create an object or a function that creates objects and returns them. So the only thing that those objects and functions do, they create stuff and then they immediately return them. So this is an example where you would like to move ownership of data.
Okay.
Yeah. So in this case, you initially allocate data in foo function. However, the memory will be removed when the main scope is exited rather than foo scope, because you transferred both the data and ownership of the data. And if you run this program, this is the output you will see. You first create the pointer, then you see the print moved out from data, because when you are moving data from one pointer to another, the original pointer is actually being zeroed out. So it's null pointer now. Then the function foo is exited. You print 10. This is the content of the memory. You print it from the main function. And then only when the main function is exited, you are deleting the memory. So this is how memory ownership works. Okay, so this is unique pointer. One limitation of unique pointers is that there is only one entity that can actually own data. So that's something that Jiro asked. Can we actually remove std move here? No, we cannot. We get a compiler error because you cannot just assign memory, because assigning memory would mean that there are at least two entities that own data. So with unique pointer, it's not possible. So that's a huge limitation. That's why we have shared pointer. Shared pointer is a memory management abstraction that assumes that multiple owners of memory are allowed. This is example. It's same example as we had before, but instead of unique pointer, we have shared pointer here, basically like everywhere in the code. And instead of std move, we have simple assignment. So in this case, when the function foo is exited, we actually have two, so here at the line 46, when we assign data to pass data, we actually have two versions, like two pointers that own data, own the same data. And
it's really just to clarify a bit, right? So first, we want to make sure that everyone's following, right? So do you get the restriction? Why is it called unique pointer? If anyone has any doubts, right? Why is it called unique? What's so unique about the unique pointer?
So if I understand correctly, it means that the ownership or whatever that is, it's localized, right? It cannot be.
Let's be more precise, right? Okay, so you allocate a chunk of memory, right? You have an object in the memory, right? You allocate something in memory, right? Let's just call it object, right?
Mm-hmm.
And then the pointer is basically what does the pointer do? It stores the address of that object, right? That memory object. Okay, so what's the relationship between this pointer and the object? What's the unique? Is there anything unique about this relationship?
The address.
I think the pointer. So there's only one pointer pointing to that address.
That's right. Yeah.
Right.
With unique pointer, right? So it only allows one pointer to point to that object. Does it make sense? One pointer variable. Right. Go ahead, Nikita.
Okay. Yes, with shared pointer, you can have two pointers pointing to the same memory location. So it's simple. And the memory location is being deleted only when all pointers are removed. So this functionality is similar to Java or Python garbage collection. So basically, shared pointer is counting references to objects, and when the number of references is 0, this is the only point when shared pointer is removing memory. So that's the basic garbage collection functionality. In this example, memory will be deallocated in the end of the main function only when the foo function is terminated. So the output is similar to the previous output, but the data pointer in the foo function is actually valid. It's valid all the time, even after we assign data. So that's the only difference. So now we have two pointers to the same memory. Unfortunately, this approach might produce issues. Let's consider this example. We have a class human. Just ignore everything here. Just only take a look at this marriage partner thing. So we have a human, and each human might have a pointer to its partner. And then we have the function marry. So basically here, the function marry accepts pointers to two humans, and it can marry it. So it's like a linked list. It can set up marriage partner of the original human to the human 2, and of the human 2 to the human 1. So we can basically marry them. So
like a doubly linked list.
Yes, exactly. Yes. So this is actually, there is a bug in this code. So if you run this code like it's written, in the main function, we only create humans, like one of them is Mike, another one Julia. So we can see Mike created, Julia created, Julia destroyed, Mike destroyed. So here everything is fine. Shared pointers work as they're supposed to work. We do not have delete operators anywhere, but the memory is managed. However, if we try to marry them, if we call this marry method after we allocate memory for them, so Mike created, Julia created, Mike is now married to Julia, so it's fine. However, the pointers are broken. The memory is not deallocated here. And this is called cyclic dependency because we have cyclic dependency in the memory. So this is the cyclic dependency graph. Can anybody hear it from the program? Like we have a human Mike that has reference to Julia, and then the human Julia has reference to Mike. So that's a cyclic reference, which prevents the shared pointer to reach 0 when they are being destroyed in the end of the program. That's why this shared pointer doesn't work. So do you see the issue? Can anybody see the issue?
72, 73, right?
72, 73, what?
That's where that talk, because that's the doubly linked list kind of thing is happening, one referring to the other one. So
yes, right. Yes.
That's the cycle.
Yes, that's the cycle. Yes. So we need to destroy this cycle somehow. And the solution is actually simple. There is a weak pointer. We just replace this pointer by weak pointer. That's the only place where we replace shared pointer by weak pointer. So we still allocate humans with using shared pointers, but pointers to their marriage partners are weak pointers. So here, that's the only change we make. And this is, so weak pointers, the only difference between weak pointer and shared pointer is that weak pointers, they do not increment the pointing count. So in this case, everything will work because the marriage partner is actually, it's not a real link. It's not like a real pointer that is not counted. So this is a solution how we can break cyclic loops by using weak pointer in here. So there is a,
So the bottom line is that if there is such sort of cyclic dependency, we cannot use the shared pointer because of that thing. So we have to use weak pointer if there is a cyclic dependency.
Right. We should use weak pointer at least in one path somewhere.
Oh, that will break that chain.
This will break the loop. Yes.
Maybe I should ask, right? So what's wrong with this cyclic dependency? I'll make sure that everyone understands.
Mm-hmm.
Why is that cyclic dependency, right, a troublemaker? Troublemaker for what?
So I guess, so for destruction, so one pointer that depends on the other depends on, so basically two pointers depends on each other. So right. If we want to run the destruction, then it cannot be done, right? It's more like a dialogue.
Mm-hmm. Right.
The simplest answer is that the pointer count, the counter will never go to 0, right?
Right.
This is the, yeah.
Right.
Yes, it's a good analogy with deadlocks. Yes, it is a deadlock.
Count, right? Because for this kind of garbage collection to work, right, you actually need to update the reference count. Right? And cyclic dependency may mess up that garbage collection, basically.
Nikita, I had a quick question too.
Yes.
Based off this question. So with the minus human, that's the deconstructor, or I don't know.
It's the human, I guess.
Yeah.
Oh, to the human. Okay. And so you couldn't solve this problem by just getting rid of the partner pointers in that function, or right?
What do you mean getting rid of?
In avoiding weak pointers, you couldn't just get rid of the partner pointer when the object was deconstructed because it would never be deconstructed at all, right? That's the core issue.
Yes, like in the yes, yeah.
Right. Right, because initially I thought we could just get around this problem by when the object is destroyed, just erase the pointer to the partner so that the other partner could then be destroyed. But the issue is that no partner will ever be destroyed, right?
Yes, right.
Or no human will ever be destroyed. Okay.
Yeah.
So Jordan, you're asking whether we can explicitly delete the pointer in the destruction.
Right. Initially, I thought that would be a solution in that tilde human to just explicitly delete the partner pointer, but it would never actually reach that function because there's always a reference to it.
Yes.
Okay.
Neither of the destructor is called. You can see the output here. So neither for Julia or Mac destructor is called. So putting like assigning and partner to NullPointer here won't help.
Right. But you
you're
could.
Right, it will never called.
But you could make a divorce function that you call before you kill them, and then.
Yes, it will work. Yes,
Okay.
This will work out.
Okay.
Sure.
Okay.
Yeah.
Yeah, we can still explicitly delete, right? I've never tried that. So with smart pointers, you can
explicitly delete SmartPointer. You can. Yep.
Okay.
Right. Okay, so I have a quick notes here, but what happens if Mike dies? But okay, we can skip it. So I think we have more topics to discuss. Okay, so those were smart pointers. The rule of thumb here, we should avoid using new and raw pointers in C++. We should use smart pointer instead. The only exception if you want to do some hardcore system stuff or you want to hack things, and we are confident enough to write our own memory management system, then we can use raw memory management. But even in this case, C++ actually provides better alternatives to new. It has like allocators and all other things that make memory management smarter. Okay, so that's all about smart pointers. Any last questions about smart pointers? If not, we will move to 3 lighter topics that we can like briefly go through. So one topic is type inference. Surprisingly, it came in C++ 11. So type inference is a feature. It's an easy feature to make code more readable. Let's say we have this code here. We have a lookup table. In C++ using templates, you have this ugly construction where you're defining the structure of your table. Like this is a lookup table that has a composite key that is in a pair of integers and strings, and it has a value where every key is mapped to. For example, it's float. Let's say we want to have an iterator to the first element of the loop, like basically a pointer to the first element of the loop, or sorry, of the lookup table, or we want to run a loop through all the elements. The constructions are pretty ugly because the iterator itself will have to repeat the precise definition of the lookup table and put the iterator here. So this is basically the type of the iterator that allows us to go through the elements in the lookup table.
And just for the benefit of the non-expert, right? So these are the STL stuff. These are the standard.
Yes, this is STL stuff.
The map, right, and the iterator.
Yeah. So C++ 11 allows to replace those ugly constructions with the keyword auto. So this looks very similar to Python in the sense that in auto, you don't need to specify the type of the value where you are assigning the data. The type will be automatically inferred during the program compilation. So it knows the type of the lookup table begin, and it will assign the same type for the iterator. It's just like kind of syntactic sugar to make code more readable and understandable. Same for loops. C++ 11 also comes with another syntactic sugar around the range-based loops. Instead of writing like a long loop, you can just do for each loop. Auto iterator, then just double comma and lookup table, so it will run through all of the elements of the lookup table. This is just nice stuff how to simplify, how to make code more compact and easier to read. So Lambda expressions. I think everyone is familiar with Lambda expressions because those days it's everywhere. It originally came from functional languages, I suppose. You can find it in Python, in Scala, in Java, and they finally came to C++. This is one of the biggest functional abstractions. So before Lambda expressions, let's say C++ defines the sorting function, where you can sort an array of data. And the first argument is the beginning of the array. The second argument is the end of the array. And the last argument is the comparator. So this is actually the function that is used to compare elements when walking through the data to properly swap the order of, properly like reorder data in the original vector. So the comparator is a function that looks like this. So instead of defining a separate function for it, in C++ 11, you can write a lambda. Lambda is an anonymous function that has no name that is integrated into the other function call. So this is a compact example, compact writing of the same example. It's the same function, which is embedded as a Lambda function. So that's pretty simple. Again, same as in Python, I think. Another example.
Sorry. So is there any semantic difference? Because it looks like pretty much same as a semantic difference, not syntactic. Semantic difference between these Lambda and Python Lambda, they look pretty similar to me.
I'm not sure about Python Lambda, and I'm not sure about semantic difference. I don't think so.
Yeah,
it might be different.
They are actually pretty much the same, but like in C++, they allows you, they request you to, like, for example, you can see the there's a bracket at line 140, right? So that bracket is, you can put like the variables from outside. Yeah,
that's an example.
Oh, yeah.
Yeah, that's a leaky ReLU example where we can access leak constant inside the Lambda. Yeah.
Yeah, but I think in Python you don't need to specify that. Yeah, you can directly use the.
Right. If it is in the scope, it can be used inside the Lambda. Yeah.
Okay,
yeah,
like any variable.
Yeah.
For C++, you have to specify that variable within the square brackets.
Yes.
Okay.
You have multiple specifiers. You can actually put equal here or and they all will be captured. Or you can specify exactly the name what you want to capture.
Okay.
Yeah, and you can also capture by reference and by copy. So those 2 ways.
Like pass by value and pass by reference kind of thing.
Yep. Okay, Lambda. Then const expression. Const expressions also came in C++ 11 and also 14. 14 actually made them a bit more robust. So const expressions allowed to compute stuff in compile time. Before C++ 11, people used to use preprocessor directives and templates in order to compute stuff in compile time. And the code was very hard to read the code. Just try to read the STL library. It's a nightmare. It's a huge library with a lot of brackets and stuff. It's hard to understand. So const expressions, you can define variable functions or even classes as const expression, and then whatever you write will be computed in compiled time rather than in runtime. That's a very simple example. We have the variable p that is const expression double. Then we have a function square, like a circle square that multiplies p by a radius squared, and that's a const expression function. And we call this function from main function. And since this function is const expression, the SQ value here will be computed in compile time rather than in runtime. And there is an interesting example here. Let me open it. That's a guy wrote a pretty large library with 500 lines of code entirely using const expressions. So this looks, for example, if you open this file, this is the library. So we can see it has like structures, it has classes, it has functions. So that's the proper C++ code, but this code is never executed. This code is executed only in compile time. So it never goes down to binaries. So that's actually pretty impressive stuff that you can write code, even complex code that is executed entirely in compile time. So what this library is doing,
So essentially, it's something like constant propagation kind of thing that compiler can do in the compile time itself.
Right. Yes.
Huh. Interesting.
But I'm not sure if constant propagation also assumes computing. I think it is. Yes.
Yeah, the compiler will try to do more, but this basically tells the compiler this is safe. It's safe to propagate the things. Okay.
Yeah. Okay, so this is just an example of what this function is doing. So it's a function to do symbolic computations on fractions entirely in compile time. Okay. So it has multiple limitations. So obviously, if you want to compute stuff in compile time, it should be finite, and also, it should be terminated within finite and pre-computed time. We cannot use things like infinite loops or goto operations, so this code will not compile. Also, compilers come with, for example, this for GCC, it comes with the const expression loop limit. So this is the maximum number of iterations it can compute in compile time. So we should not exceed it. Also, data should be of a literal type, and many other limitations. So it's not actually that easy to write code that you can run in compile time. But C++ 14 made some significant progress towards relaxing those limitations and allowing more things to compute in compile time. Static cast is a type of type converters in C++. There is static cast, dynamic cast, const cast, and reinterpret cast. So static cast is a way to perform explicit type conversion in compile time. So for example, we can convert ints to floats, floats to ints, different ints of different precision, class A to class B, if they have conversion operators. We can convert references and pointers to objects that come from the same inheritance hierarchy. Actually, there is 10 cases when we can use static cast. So that's the simplest form of typecast. This is an example. Like we want to cast a variable A that is integer to B that is float. So we can do it with static cast.
You want to explain what we mean by static B, and static?
Right. So in order to explain what is static cast, let's show what is dynamic cast. So static cast is actually the safest typecast that we should try using first. But sometimes it doesn't work. So if it doesn't work when compiler cannot understand the relationship between types in compile time. So for example, if you have polymorphism, and if the dependencies between different classes, like the inheritance hierarchy of classes, is so complex that compiler cannot capture it in compile time, static cast will fail here. Static cast won't be able to understand the relationships between types. And that's where dynamic cast comes from. This is an example. We have a class A, then we have a class B. Then there is class D that inherits both A and B. So in this case, the inheritance hierarchy looks like this. The class D inherits A and B. So the classes A and B, they are not connected to each other. They do not have any relationship. That's why if you try to run static cast here, the static cast will fail, because for compiler, those classes are completely different. It's like apples and oranges. You cannot cast them. But actually in runtime, it turns out that they are both inherited by class D. So they have a relationship over the class D, that they're actually related. That's why dynamic cast here will be passed.
Nikita, I didn't understand I understand this why the static won't work, but how the dynamic cast will solve the problem? Can you just repeat that part?
Yes, so for static cast just simply looks at classes and it sees that they are different, apples and oranges. It will fail. So that's right. But dynamic cast look at the classes in the inheritance graph. So let's say this is a graph, this is actually a graph, and this graph might be very complex. So the dynamic cast looks through the whole inheritance graph and sees if there is a reference, there is a link that connects to classes. And if there is a link, then it can be casted, and then the cast will succeed.
So because here D inherits both A and B at runtime or at the dynamic execution time, the runtime environment will figure out that A and B are related.
Yes, they're related. Yes, exactly.
Okay.
So it's safe to cast A to B because the memory that you might use in A or B, it will be also shared by D. So this memory will be connected. That's why you can actually safely cast it. This is the thing. So if you remove the link, for example, if class D only inherits B and does not inherit A, so it's like this. In this case, dynamic cast will fail because those are completely unrelated. Does that answer the question that people had?
But does it mean if I can use static cast, then I can always use dynamic cast, or it's not the case?
Yes, it's the thing is that dynamic cast is originally designed for those types of casting when you have inheritance hierarchies. So you cannot use dynamic cast with the literals, for example, only with pointers to objects. There's some limitation that limits dynamic cast to the use cases where you actually need it.
And I also think that with the static cast, in the compile time, if compiler can impart something, then it can do better optimization. But in cast,
probably, yes.
dynamic cast, it's just leaving everything to the runtime. So that sort of optimization may not be possible.
Yes,
Exactly.
right.
Yeah. Right.
Okay.
Static is always better for compilers.
Right.
Yeah.
Okay.
So there is also reinterpret cast. This one that is dangerous. Like this one that you can cast like apples and oranges, apples to oranges, completely unrelated classes. But here you, as a programmer, you need to ensure that you know what you're doing. So next time we can discuss reinterpret cast in details if we have this talk.
Yeah, you can also just directly explicitly cast, right? So without even using this dynamic reinterpret.
Like in brackets?
No, I think you can just use the So use brackets. Right?
Yeah,
Cast.
yeah. Actually,
That's
yes, it's called C.
Right? That's also dangerous, right? Basically, you're assuming that the memory layout of these two objects, right, are similar.
Yes.
Right.
Yeah. That's why in C++ you should not cast it like using brackets. You should always try to cast it via static or dynamic cast first. And if you really need to cast like to relay out memory, then you can go dangerous.
Right.
Yeah.
Right. Dynamic cast is actually does something called RTTI or something, the runtime type identification maybe. Yeah.
Right.
I have a question. Is the inheritance direction matter here? Because I think for A and B, they can also be totally different.
What do you mean they can be different?
Like you can write A and B to be totally different classes.
Yeah, it's still you to control to manage the correctness of the program. Yeah.
Yeah.
So when you cast, you have to call the right API.
Yeah. So the dynamic cast here will not check whether.
But it may still.
No, it won't.
No, like.
But I don't think you can find problems here. Because if you static, yeah, sorry.
Maybe the newer version, but not the one. I think there's still a way to fail it. But I might be wrong. Depending on
like
how you use the pointer, right? How you use the casted pointer. Anyway.
Yeah, because I'm just like don't quite understand why they, as long as they can traverse this graph, they can just say whether there's a direct path from A to B. But actually, from the graph here, like because the inheritance is actually directed. So for me, there's no direct path from A to B. If we assume that edges has directions.
Yes, there is actually a relationship, and you can see it here when we call the move method. You see the move method is defined in A, B, and D. And
yeah,
if you,
But what if you change A and B to be totally different classes or structures?
What do you mean totally different?
So Nikita, let me translate for you.
Yeah.
I think what she's asking is, we look at line 268, right? Instead of newing a D class, so we are doing line, right? We create a new class for D, right? But new class of D. So yeah, it's asking like if we new A class, what's going to happen for the dynamic class?
Oh, if B is equal to new A.
Right, and then you dynamic cast it to let me no. So
you
sorry,
cannot do this.
I meant B instead of A.
Yeah.
If you do a B class.
So if you do B here.
No, do B in 268.
Oh, I see. New B. Yes. So then PB will be just B. Okay.
Right. So she's asking, right? So what's gonna happen?
I see. It's a good question, actually. Interesting question.
So this is where I'm saying this may fail, right?
Yeah, I think you cannot cast in this case.
I think you will fail here. Yep.
Oh, okay. I didn't notice that's D here. So okay.
Yeah, it's D here.
Okay.
Yes. Because the thing is that we allocate the PB now is reference to the memory that is a part of D class, which is shared between A and B. That's why it's safe. But if you put B here, then then I think the dynamic cast will fail.
Then I think the compiler will actually check there's a path from D to A, not from B to A, right?
No, but if you do dynamic cast, the compiler will not check.
Yeah.
Okay.
Just throw a runtime error or something at some point.
Compiler just throw RTTI. I think that's the runtime error.
Runtime.
Yes, it has thrown an exception or just returns null pointer.
Could be an exception.
Oh, okay.
Yeah.
Okay, thank you.
Yeah, sure. I'll actually try it out now, but I think it will return. I think it will fail if you just try to cast it B to A without affecting D.
Mm-hmm.
Yeah.